Okay, so a plank A to B has a weight of 100 newtons and a length of 4. The plank rests horizontally in equilibrium on two smooth supports C and D. A to C is X, C to D is 0.5. Okay. Now this uniform plank means that the center of the weight, which will be, let's just say if it's the 2 meters is there, that's where the 100 newtons, that force of 100 newtons will be coming down the center of mass. Okay, so it goes here, the magnitude of the reaction of the support on C, so the magnitude of that, the force pushing that up is 75 newtons.
Why do you look at the centre of mass in the middle?
Because of uniform.
Oh,
If it didn't say uniform, we need to find, if it's non-uniform, we need to find out where it is. But because it says uniform, you go for the centre in the middle. Okay? Now, if that's 75, you know that the force that's being pushed here is 25. Because it's in equilibrium, these are balancing. Right, so, I might answer the question. Modeling the plank as rigid. Rigid means it doesn't bend. Find the magnitude of reaction support on D. Right, I did that automatically. We all understand that they horizontally they're going to balance because it's in equilibrium. Yeah, so that's a nice easy marker, 25 newtons. Then it goes here, find the value of X. How far is that? Now, first of all, this force is being reacted, is going that way, anti-clockwise. That is also being pushing upwards, is going that way, anti-clockwise, and this force is going clockwise. Okay, so the anti-clockwise must equal the clockwise because it's in equilibrium. So if I put this formula as X, so it's, remember, moment is equal to the force times the perpendicular distance. Now if I take the moment at A, for instance, I know that this is going anti-clockwise, so I know that 75 times X is the distance. This is the perpendicular distance to this force, so it's X times 75. And this distance here is going to be plus X at 0.5, which is going to be times by 25. Okay, so that distance from A to D is X plus this half a meter, and it's times by 25, the force pushing it up. It's going to balance with, it's going to equal this force coming down, which is the center force, so it's going to be 2 meters times 100. So you should set that equation up first. Once you set that up, you got 75x plus 25x plus 12.5 equals 200. Take that to the other side, so you got 100x equals to 87.5. 187.5, sorry, 90, yeah, and then divide that by 100, so X would equal 1.875 meters. So X is 1.875 meters from that edge. Now it goes here, find the, right, so that's, any questions on part 2? We're good? Okay. Now, it goes here, stone block. Now I'm going to change the colour on here so I'm not confusing it. So, a stone block, which is modeled as a particle, is placed at the end of the plank at B. And the plank is on a tilting point about D. So what does that mean? So that weight, the weight of that is going to be mg is coming down on here. Okay. Now, when it says it's at tipping point here, this is gone. Okay. There is no more force applied here because that tipping point at D, there's only that and that in relation. If you imagine something balanced on something, and then this is about to move, it gets lifted here. So because it gets lifted here, there's no actually reaction at this point. So there's no point supporting it. It's off that support. It's about to tilt. Okay, tipping point. So with that in mind, these are the only two forces taking effect. Okay, again, if I take the moment, so this is 100 coming down that way. This is mg coming down clockwise. It's going to go. I'm going to take the moment at A, and this is the only force reacting to it going upwards. Okay, and I'm going to rub that off because I don't know. Find the weight of the block. So this is the only force that's going down, and that is pushing it upwards, this force here. But it's about to tilt, so it's still in equilibrium here. I'm just trying to see something. Right, now I did say I was going to take the reaction at that point, but I don't know some facts about D. So the best thing is, rather than taking the moment from A, because I don't know what the force is happening at D, the best thing will be to take the moment, in this case, take the moment at D. Because when you take the moment at D, you don't need to know what the force, we don't know what force is pushing that, balancing that with. So therefore, it's best to take the moment at D so we know any forces which are taken at that point. Okay, so that means I do know the position of D, however, because I know that X is 1.875. So D is add half onto that, so you got 1.875 add 0.5. You know that D is the position from that to there is going to be 2.375. So if the center is at 2, this distance here is going to be naught. This distance, I'm just going to write it here because there's a lot happening here. 0.375. Okay, so now once I've done that, this is going to be moving downwards, and this, because it's going down and it's force from there, let me just have a look at this. So that's going to be there, that's going to be going up. Okay, that's going to be the position of this weight, because that's tilting with that. That is going this time, this is changed. I'm just going to rub that out. It's the center of mass in this case, which is here, is going to be acting going upwards. That's going downwards. Just give me 1 second. No, my bad. It's still going to be acting downwards, the weight will, from there. But this will be balancing it off with this way. Okay, so that will go in anti-clockwise, and this one's going clockwise. So they just in terms of balance. So at D, you're going to get 0.375 times the weight, which is 100. Okay, it's going to equal this weight coming down. Now, if you know that was 2.375, if I do that and subtract it from 4 meters, the distance from D to B is 1.625 meters. So that's going to be 1.625 times mg. Now I'm going to put m but the G is 9.8. Okay, because we just, oh sorry, can I just say, because it's just talking about weight, I'm just going to call it mg is the same as weight, so I'm just going to times that by W. Okay, if I wanted to find the mass, then I could put G as 9.8. Now if they're balancing each other, I just need to subtract that by 1.625, and therefore if you do that in your calculator, if you do 0.375, multiply that by 100, share that by 1.675, you'll get a weight of, oh, not nice, 22.39. I'm going to call it just 4 newtons. Now you've got that weight. It goes to explain limitations of the modeling. Stone as a particle. Now you don't know how big the stone is, so you've got to talk about the dimensions. Okay, and where the center of mass lies. We take it very simple. We make, could be depending on how big that stone is. You have to talk about dimensions, which is a limitation on here. And Planck being rigid, we're assuming that this Planck does not bend. Okay, we're going to talk about the bend, flex in the rod. Okay, if it flexes, then that takes them into account.